So this is a quick video to really kind of make some connections between the what a derivative is and a lot of the notation that we'll be using. I'm really just hitting kind of the main notation right now. So I've created a box here that kind of, I don't know, I think I'm trying to kind of summarizes all the stuff. I'm trying to help to organize these ideas in your mind. So the first column is the original function, the second column is the derivative, and the third column is the second derivative. So a second derivative is just when you take the derivative of a function once and then you take the derivative again. And so I think you've seen this notation so far. Obviously you've seen f of x before, that's just function notation. So when we're taking derivative, one way to express it is this little prime here. So f prime of x is the derivative of f of x, and f double prime of x is the second derivative of f of x. And actually you could keep going and take derivatives. In fact, at some point the primes get too hard to notice or to keep track of, so we just put a little number in parentheses. This would be a third order derivative. In other words, I've taken the derivative of the original function 3 times. Okay? So then another notation, this is called Leibniz notation, is and another way to express the original function is just a y value, right? That's what the original function is. That's what f of x stands for, is the y value. And so the derivative, another way to express the derivative is, this is Leibniz notation, where you put dy dx. Now this is a nice notation because it reminds us of exactly what we're doing. The d actually stands for delta. So this is reminding us that our derivative is just a change in y versus the change in x. So often you'll see me using this notation. I actually use both, but so be aware of both the f prime and the dy dx. Now the one that's a little bit tricky is the second derivative, and this notation looks a little bit funny. People have some trouble with it. It's d squared y over dx squared. And the reason it's written like that is because you're taking the derivative twice of y with respect to x twice. That's why we're squaring the derivative on top and squaring the x on the bottom. Now this notation becomes especially helpful when we start getting situations with more than one variable, because it's important when you're taking derivative to know what you're taking the derivative with respect to. So this is comparing the change in y to the change in x. We could compare the change in y to change in t if t is a variable in the situation. So this notation really helps. When you write it just like this, this is assuming that whatever the dependent variable is on top, and usually the variable in here is the variable on the bottom. So then also, if you're trying to evaluate at a certain place, right, you should be familiar with this notation. This means that I want to plug in 2 for x and find out what y is, right? Or evaluate the function at 2. So using both notations, this is the way this is very similar to that. You just put a 2 in there, and that would mean that I'm evaluating the function at 2. And if I wanted to use it, express that using Leibniz notation, this is how you do it. So you write dy dx just like you normally would, little line, and I'll put at x equals 2. So these two mean the same thing. And then of course that's how you'd write it with the second derivative also. So then some other connections you should make. I think this has come up maybe before somewhere in our discussions, that if the original function is the position function, then the derivative of that would be the velocity function, because you're comparing change in position to change in time, which is velocity. And if you took the derivative again, that would be comparing the change in velocity to the change in time, which would just be acceleration. So this is trying to get you to go down that path of start thinking about what does a derivative mean in context. So in general, the original function is the dependent variable. The derivative is the rate of change of the dependent variable compared to the independent variable, just like it's expressed up here, change in y versus change in x, right? And then of course the second derivative is the rate of change of the rate of change, because this is a rate of change and we're just taking the rate of change of that rate of change. Some other thing to keep in mind is the original function, if we think about in terms of the graph, this is the y coordinate, right? The original function gives you the y coordinate. The derivative gives you the slope of the graph, and the second derivative gives you the rate of change of the slope, which sometimes that's expressed in concavity. Think about this. If you have a slope that's getting less steep, that would be concave down. If you have a slope that's getting more steep, that would be concave up. So concave down means that it's the curvature. In order to, you could think of it, in order to leave the cave, I have to go down. Concave up would be in order to leave the cave, I have to go up. Okay, so if we're thinking strictly of the graph, the function gives me the y-coordinate, the derivative gives me the slope, and the second derivative helps me determine concavity because it's the rate of change of the slope, right? So this would indicate the slope is changing. It's getting less steep. Here the slope is getting more steep. So that's what the second derivative tells us about, is the rate of change of the slope, how the slope is changing. So that's that summarized for the most part a lot of the notation at the top, and then some of these ideas that you're going to be dealing with this week, as far as trying to get a handle on what does the derivative mean in context. And also it's really good to pay attention to units, because the units can really help us determine what the derivative means. So for example, if I have a f of x gives me the let's say it gives me the amount of, let's say I'm painting a house. Let's say f of x gives me the amount of paint used in gallons. And let's say that, instead of f of x, let's go f of t, because we're going to say that t is time in minutes. So the original function, you plug in a unit of time in minutes, and you get out the amount of paint used in gallons. Okay, so then the question would be, what is f prime of t then? And so think about units. So remember, derivative is the rate of change of the dependent variable compared to independent variable. So the dependent variable is measured in gallons. So this would be change in gallons compared to change in time, change in minutes. So the derivative of this function is comparing the change in gallons to the change in minutes. So that would be something like the rate of paint being used, like how fast the paint's being used. That's what the derivative would be. Okay. So just thinking about the minutes, because this is gallons per minute, would be a way to say this. That's how many, that helps you to see that that's what the derivative means. So if I was to say f prime of 2, what would that mean? That would mean the rate at which the gallons are being used 2 minutes into the painting. So the 2 represents 2 minutes after starting to paint. And then the f prime would be gallons, or change in paint volume, I guess, if you will, compared to change in time. So in other words, how fast is the paint being used up 2 minutes into the time of painting? And of course the 2 is important because it might not be the same all the time. Now if the guy's a steady painter, it might be, this might be a constant value. It might be just always, I don't know, 1 gallon every 10 minutes or whatever. So this might be constant, but it could be that that it's fluctuating, because if he's going through a hard part, a more delicate part, he's using less paint. And if he's going through maybe a bigger stretch, it's easier to put on a bunch of paint. So this is probably changing. So the actual derivative would be different depending on what number we plug in there. So the 2 is telling me when I'm checking the derivative, and the derivative is the change in paint volume per time. So how fast the paint is being used up. Okay, so that's just an example. There's a bunch of worksheets in the week 3's module that will really help you to kind of get a hold of this and practice this a bunch. So get out there and start practicing.